Okay, so we've already talked about Nash equilibrium in this environment, and given previous chapters, you probably know where we're going next. We will be talking about subgame perfection, and in the context of subgame perfection, the thing we're going to talk about is the one deviation principle. So what the one deviation, not principle, property, what the one deviation property says is that no player can increase her payoff by changing her action at the start of any subgame in which she is the first mover, given the other player's strategies and the rest of her own strategy. So what you're considering is only one deviation. So if there are multiple games being played, let's say a sequence of Prisoner's Dilemma games, all you're considering changing is the player's strategy for one period and not the rest. Holding the rest constant, holding constant the other player's strategy as well. And we show that if this holds for all subgames for this player, and for the other player's strategy as well, if the one deviation property holds, then you have subgame perfection. So if the one deviation property is followed, that implies that the equilibrium is subgame perfect, and if the equilibrium is subgame perfect, then that implies that the one deviation property holds. Again, the one deviation property says that the equilibrium, the strategy profile being considered, is robust, so it's better than what this player could achieve by deviating once from her existing strategy. It's very easy to show that subgame perfection implies the one deviation property, simply because if the game is subgame perfect, then at no point, at no subgame, does the player want to change her strategy in any way whatsoever. Therefore, the player does not want to change her strategy for that given action or at that given node as well. The opposite is a little more work, but we'll go through it. So let's say player 1 is moving at both of these periods. And the payoffs are W, X, Y, and Z. The options are C, D here, E, F, G, H. And suppose that C, E, G follows the one deviation policy property. Also, in case you want to pause and read it more carefully, the one deviation property is given here. Right, so what we consider is the possibility of the players, for the players to change their action at the start of the subgame. There are 3 subgames here. This is a subgame, this is a subgame, and this whole game is a subgame. If CEG follows the one deviation property, then that means that within this subgame, and this subgame, player 1 has no incentive to change her actions. If player 1 has no incentive to change her action here, then that means that W must be at least as large as X. If player 1 has no incentive to change her action here, we're considering CEG, by the way. If player 1 has no incentive to change her action here, it means that Y must give a utility that's at least as large as Z. And if player 1 has no incentive to change her action here, then that must mean that W is at least as good as Y. right? Because when player 1 is considering to change their action between C and D in this subgame, you're holding constant the continuation of the game. So W is at least as good as X, and W is at least as good as Y, which is at least as good as Z, which means that W is at least as good as Z as well. So W is the best outcome here. And so if CEG follows the one deviation property, then it also shows that this equilibrium is subgame perfect, because if none of these subgames would player 1 have any incentive to deviate. Notice that here we've only considered player 1's strategies. There is no other player for this game. But you could insert another player, you could give player 2 moves, but as long as you're holding player 2's moves constant when you're considering deviations by player 1, then you know what the continuation of the game is. So adding another player doesn't actually change this logic even at all. What you're comparing is continuations. What else? So subgame perfection requires a Nash equilibrium in every subgame, and those subgames can be large, it can be really long. What this allows you to do is to break things down and show that if you are playing optimally at every given period, then you will also be playing optimally over the game at large. Okay. So this works for all finite periods. So in all finite periods, the one deviation property holding implies subgame perfection. Should be perfectly clear though, this only works for games with perfect information. So if you have any uncertainty or any imperfection in information, like you don't know what previous players have done and so on, then this does not hold. Let's consider the infinite period version of this game. That's a little more difficult to show precisely because here we relied on the fact that we could work our way upwards from the end of the game. In an infinite period game, there is no end of the game to work our way up from. But this property still holds. The way we show that this property holds is that, well, one, if something is subgame perfect, then the one deviation property has to hold. The other direction is, again, more tedious. And the way we show that is, let's consider a strategy being played Si by player I, and let's say that S prime I is a better strategy, right? It's that Si is not subgame perfect. So let's say there's some path that's being played, and that path is Si, and you could deviate from that path and choose S prime I, and that's a better path. If you have a discount factor that is strictly, so if delta is strictly between 0 and 1, eventually along this path, or along this path, changing your actions doesn't have much in terms of ramifications when you're looking at time t equals 0. Right? When you're looking at the beginning of time, after enough time has passed, if you're changing your actions, if you're thinking about actions 100 years in the future, that doesn't really impact your net present value, how you evaluate those different strategies, because your payoffs from that future are just so far away that once they're discounted to present value, they're not worth much. So if there exists a better path for you, a better strategy for you, S prime I, then there also exists a better strategy that looks like S double prime I, where after time period t, you've reverted back to Si. And then you can just use the fact that after time t, both paths give you the same utility, so you can ignore them when you compare these two paths and your utility from these two paths. And this is the structure you use to show the fact that the one deviation property implies subgame perfection even in the infinite period version of a game. I'm not going to be testing you on the proofs. To be fair, this is not a precise proof. What I'm giving you is the structure used to prove this. What you do need to remember going forward is the fact that if you want to show that a Nash equilibrium is subgame perfect, it is sufficient to show that there is no profitable deviation for any player, where the profitable deviations you consider are single deviations, where you're only deviating for one period and holding the rest of the future path of that strategy constant. Then if you can show that the strategies are immune to those one period deviations, that there don't exist any profitable one period deviations for either player and for any of the periods in which they have a turn to move, then that is sufficient to show subgame perfection. And so that's it for this video. Thank you.